In the previous video, we were looking at the difference between the observed and the expected rotational velocities of stars in galaxies, and we identified that a possible explanation for the difference is dark matter. Now, in that situation, the dark matter would actually tend to exist as a halo around the galaxy itself, but we need to understand what dark matter actually is, and we basically consider it as just being not our normal luminous or baryonic matter. So not matter that's made up of baryons. And the reason why we call it dark is because it emits no radiation. So by not emitting any radiation, the word dark there is just indicating that we can't easily detect it, and means that we can observe evidence that it's there, but we can't actually identify what it is because we can't detect it directly. So, as I said, there is evidence that it exists, and we'll have a look at some of that evidence now. And we've already seen that first situation, the variation in the rotational velocities. So rotational velocity curves can be explained by considering a halo of dark matter around a galaxy. So the reason why that would work, by having extra mass around the outside of the galaxy, that means that the density of the galaxy is not quite what you might expect, and so you've got a large mass surrounding the galaxy, and so as a result the rotational velocities are affected by that amount of mass. Second one is the velocities of galaxies orbiting each other. So when we have galaxies in clusters, they will tend to sort of rotate around each other, and as a result there's certain properties that we could observe, and the observations that we make don't match with the matter that we can directly detect. And the observations that we're talking about there being the radiation that they emit. So there's much less light coming from them than the matter that we can observe. So less than they should when considering the masses, or the amount of mass that their velocities would indicate is present. So similar sort of idea to what we're looking at with the rotational velocities of stars. The rotational, or the orbiting velocities of these galaxies doesn't match the matter that we can directly observe. The third one then is gravitational lensing. Now, gravitational lensing is about the bending of light as it travels past a large mass, and if we look at gravitational lensing of distant objects, light is being bent by amounts that don't quite match with the mass that we can observe. So it's being bent by galaxies, but it's more than expected by the luminous mass, or the luminous matter. So again, the idea of what we can see, so the bending of that light is more than the luminous matter of the galaxies would suggest should occur. The last one is about elliptical galaxies and the gases that they have orbiting around them. Those gases, so call them halos, they're hot gases that emit X-rays, and that might not sound all that interesting in and of itself, but when you consider that those gases extend well outside the galaxy itself, it doesn't really seem to link with the mass again, the mass of the galaxy that we can see, and so the galaxies must have much greater mass for those gas clouds or the gas halos to be bound to the galaxy. So there's the evidence that we have for the existence of dark matter. We now need to have a quick look at what some of the possible candidates are. So the exact nature of dark matter isn't something that we can identify at this point, but there are some possible candidates that could account for dark matter. So currently unknown what it actually is, or how it what it's actually made of, but a couple of candidates that you do need to be aware of. So these are explicitly referenced in the syllabus. And they've got kind of interesting names, and they're almost sort of opposite to each other. So the first one, the first category are machos. Now that stands for massively, so the MA comes from massively, and in this situation, when we're talking massively, we're talking things with mass, not necessarily things that are extremely large. So massively compact halo objects. And so with these machos, they are high density objects, and if you think about the high density objects that we've already discovered or discussed, things like black holes, neutron stars, and brown dwarfs are good examples. But they would be at the end of their lives, and that would be because we know that they'd have to be at the end of their lives because they're not emitting any radiation, and they'd also have to be a long way from luminous matter. So they're not able to be detected because of the fact that we can't see them, so there's no radiation being reflected off them. Now the presence of machos can be detected by gravitational lensing. And problem though with these machos is that while they're possible candidates, there may not actually be enough of them to account for all of the observations that relate to dark matter. So all of the observations that we listed above, there may not actually be enough of these compact, high-density objects to account for those observations. So there's the first type of candidate. The second candidate is somewhat equally strangely named. They're called WIMPs. Now WIMPs are weakly interacting massive particles, and again that word massive, we're just saying that they have mass, not necessarily that they are big. And when we're actually talking about particles here, we're saying that they're actually quite small. So the particles that we're talking about are subatomic particles. and they're not made of baryonic matter, or not made of normal matter. So with these WIMPs, they can pass through normal matter with very little interaction. So we actually already have a couple of candidates that could that sort of fit that description. We'll talk about those in a second. The problem again, though, is that we would need a massive amount of these WIMPs in order for the observations of dark matter that we mentioned earlier to be accounted for. So again, if you think about things like the rotational velocities of stars, we'd need a ridiculously large amount of this of these WIMPs in order to explain that difference between the observed and the expected. So not a particularly good solution, given that there's seemingly not enough of it, or there wouldn't be enough of it to account for those observations. But still, it's got one of the best options that we've been able to come up with so far. Now, as I said, we've already got a type of matter that could be classified as a WIMP, so a neutrino, or neutrinos are candidates for being WIMPs, but we do have a couple of other hypothetical particles, so not guaranteed that these ones exist. No evidence that has actually been found experimentally yet about these particles, but they could possibly be dark matter. So axions and neutralinos, but as I said, they have yet to be discovered experimentally. So there's the detail about dark matter. The next video we're going to have a look at also at dark energy, so another type of solution to some of the observations in the universe. We'll get onto that in the next video.